introduce himself.
All right, well, thank you for the introduction, and thank everyone for joining me this morning. My name is Marc Newlin, and this talk is Hi, My Name is Keyboard. And today I'll be talking about a bunch of Bluetooth bugs that I had disclosed in the last few months. There are keystroke injection vulnerabilities affecting most major operating systems, and then some bugs in Apple keyboards and macOS to extract Bluetooth link keys from existing paired keyboards. A little bit about myself. I work as a reverse engineer at SkySafe, so I have the pleasure of getting to spend my days doing reverse engineering on drones, like firmware and communication system RE. I also have a history of publishing keystroke injection bugs. If you followed IoT security back in 2016, you may have seen some bugs that were under the MouseJack brand. This was a collection of 16 or 17 keystroke injection bugs and keystroke sniffing bugs I found in a lot of non-Bluetooth wireless keyboards and mice. And I also have a history of doing competitive engineering challenges because I'm kind of a glutton for punishment. I've competed in 3 DARPA competitions. The first one was reassembling shredded documents, and I competed in their 2 software-defined radio challenges. And I also have this feature where if I own a device that has a radio in it, I am obligated to hack it. I've learned that I need to just buy 2 devices so I can have one to use and then one to break. And over the last 9 years, I've found wireless bugs in all of the vendors on this list. But I haven't published much in the last several years. And last year, I went and attended Hardware I/O in Santa Clara. And it was the first multiple-day conference I had attended since COVID started. And I really forgot how much I enjoyed just coming to these things and nerding out with all of my hacker friends. And so at Hardware I/O, I decided that I was going to do more hacker conferences. And for me, that is publishing, research, and hacking things. And at Hardware I/O, I watched some good talks and really had a blast. And I just had this thought that it'd be fun to hack some gaming keyboards. And it seemed like a good idea at the time. So I purchased gaming keyboards from several of the top-tier vendors, 4 or 5 keyboards I purchased. And I got to work on doing some RE. And my hope was that in the time that had passed since MouseJack, all of those vendors that make those kind of shoddy proprietary protocols, I figured, the public shaming I gave them would have caused them to improve their security or at least care about it. Unfortunately, that didn't turn out to be the case. So the first 3 keyboards I looked at this time were completely unencrypted physical layers, and I was kind of fun at first, but then it got boring because I really wanted a challenge, and they did not offer that. Then I came to the Alienware AW920K. This was the one keyboard that at least made an attempt at security. So when I first purchased this, it had just come on the market, so there were no firmware updates available, so I had no firmware to download and reverse engineer. I took a quick pass of some hardware RE, and I noticed that they had the anti-debugger protections turned on their NRF SoCs. I'm sure there are ways to bypass that, but that's not what I was interested in doing. And so I decided to try some fuzzing of the USB dongle for this keyboard. And so I made a simple USB control transfer fuzzer. And what that means is, a Python script which sends HID commands to the dongle and then single, double, or triple bit flips on those known HID commands. And what I found was after about 30 seconds, the dongle stopped responding. So I unplugged it, plugged it back in, and it was not enumerating on the host. Amazingly, though, the fuzzer had erased 2 pages of flash memory from the bootloader. And in doing so, it had left SWD enabled on the dongle. So I was able to dump flash memory after this fuzzing attempt. But because most of the bootloader was gone, I couldn't really use it anymore. And so I contacted Dell. I wanted to find out if they could sell me another dongle. But they didn't have any way to pair new dongles or to sell me a single one. And so my only option was to spend another $300, buy another keyboard, and it just did not sound fun. So I decided to move on from gaming keyboards. But before I did, I took another quick look at this Alienware keyboard and did a little bit more RE. And my hope is that somebody will continue down this rabbit hole of hacking these gaming keyboards because they're kind of hilarious, but I didn't disclose any of the gaming keyboard bugs, and so I hope somebody will complete that work and get some inspiration there. I did find that there is an AES key that lives above the application in Flash. It's a 16-byte, appears to be static value. 5 bytes of that get replaced with the 5-byte address of keyboard dongle. That becomes a 16-byte AES key, which encrypts the data going over the air. I think that key is static, but I haven't verified this on another dongle. I also noticed that they now have firmware updates available. They're encrypted, but they're encrypted using a key that is derived entirely from the size of the image in the update. And so there's a script I have on GitHub, which you can use to then decrypt those firmware updates if you want to do some exploration there. But after these gaming keyboards proved out not to be fun, I decided to look at two brands that I've always avoided. It was Bluetooth and Apple. And during the MouseJack work, those were all non-Bluetooth devices. And people would ask me what I recommended from a standpoint for a secure keyboard or a secure mouse. And I recommended using a Bluetooth device because, from my perspective, I thought Bluetooth was secure. All of the research I was aware of were things like cryptographic attacks or memory corruption bugs, and I figured that meant that all of the low-hanging fruit in Bluetooth was gone. And similarly, Apple has always terrified me, because everybody thinks they have really good security, people speak very highly of them, and I've been intimidated, and I was scared that I would try to hack an Apple device, or I would try to find some Bluetooth bugs and I wouldn't be able to. And I let my intimidation and fear get in the way of actually finding out. So for the last 8 years, I've just kind of assumed Bluetooth is secure and so is Apple. And it turns out I was wrong. So I decided to buy the cheapest Apple keyboard I could. This was the A2450, and it's around $100. But before we get into these Apple bugs, I want to spend a few minutes and just go over some Bluetooth concepts and some HID concepts. I found at the start of this research that I thought I understood Bluetooth, but what I really understood was the BLE physical layer and the Bluetooth Classic physical layer. But the application stacks I was clueless about. And so I had to learn quite a bit of kind of rudimentary Bluetooth stuff for this work. So the first concept is called a Bluetooth profile. And this is basically an application layer API that describes how to use Bluetooth for a specific use case. So you have profiles for things like keyboards or audio devices or networking devices or storage devices. There are approximately 80 profiles defined in the spec, and most Bluetooth hosts will support between 10 and 20 of these profiles. And for Bluetooth keyboards, they can operate over BLE or Bluetooth Classic. These are distinct physical layers, distinct protocols. So all of the vulnerabilities in this talk are specific to the Bluetooth Classic HID profile. I have not looked at BLE, which is the HID over gap profile keyboards. It's possible they're secure, maybe they're not, I'm not sure. I've only looked at the Bluetooth Classic. So to find out what profiles a Bluetooth device supports, use something called service discovery. So when your Bluetooth device is in discoverable mode, it runs a service on L2CAP port 1. Other devices can connect to this service and query the profiles that are supported by that device. From an implementation standpoint, if you have a Python script running on a Linux machine, you can connect to the SDP service on a target Bluetooth device very simply. L2CAP is this layer that you communicate over. It's similar to TCP. You address with a MAC address of the target Bluetooth device. You have a port number, and then you can create a socket and send and receive packets. Bluetooth keyboards using the HID profile use two L2CAP ports, 17 and 19. There's a control channel on port 17. The control channel is used for high latency configuration-related commands, and the interrupt channel is used for low latency things like keystrokes and mouse movement coming in from the peripherals. On top of the control and interrupt channel, you have HID reports. HID reports are basically a TLD-like structure, which allows you to send HID-specific information, but also application-specific information. Input and output reports are data going to and from the device. Feature reports are the host setting essentially a persistent key value store on the device. So feature reports are used for long-term configuration in general. So assuming that you have a client device, which is paired with a Bluetooth host, if you want to connect and pretend you're a keyboard, it's pretty easy. You just connect on the control channel on port 17, the interrupt channel on port 19, and according to the Bluetooth spec, as soon as you are connected on these two ports, you are officially a keyboard. So once these two ports are connected, you will have the host enumerate you as a keyboard, and then you can inject keystrokes. But this requires that you are paired with the host. And I kind of misunderstood Bluetooth pairing when I started this work. Pairing is this concept of generating a link key. The link key is used to encrypt traffic between the two devices. And pairing itself is a temporary process. And bonding is the process of saving that key to the device, so remembering the link key for the next session. And so what people commonly refer to as pairing is really pairing and bonding. And during pairing, each device can define a pairing capability that it supports. Pairing capabilities are define the authentication mechanism that you can use. So this might be numeric comparison, where you have both devices display a number, and the user has to acknowledge that the number is the same. You might have one device display a number, and the user has to enter that into another device. But then you have the pairing mechanism called no input, no output. And this is basically saying I do not support displaying any numbers or entering any numbers, and so it provides no authentication. And the core problem of the keystroke injection bugs I found are that hosts allow you to use this authentication-free pairing mechanism and just kind of pair yourself with a host and send keystrokes. You can also do pairing out of band. This is when you exchange the link key over a channel that is not Bluetooth. So that's commonly USB or NFC. You might also have devices which are paired to the factory, where you write the link key to NVRAM, for instance. Okay, so with that background on some Bluetooth and HID concepts, let's take a look at these Apple keyboards. So when I first cracked open this keyboard, well, literally cracked open the first one, I actually broke the PCB on the first keyboard, and so I had to buy a replacement. And I decided to use a little bit of a lighter touch. And so I took this USB control transfer fuzzer that I had pointed at the Alienware dongle, and I pointed it at the Magic Keyboard. And after about 30 seconds, it stopped responding to my requests. So I unplugged the keyboard, plugged it back into my Linux machine, and it did not enumerate. And at this point, it seemed kind of crazy, because how could you, brick an Apple product with 30 seconds of a simple fuzzer? And it turned out that what I thought was a brick state was really temporary. If you powered the keyboard off and then back on, it would come back to life and behave as normal. And it turned out what my fuzzer had discovered was just some documented functionality in the USB spec and the HID spec. So in USB, you have something called descriptors. These are what I thought were read-only properties, where a device will advertise things like its name, serial number, manufacturer, different characteristics of the endpoints it supports. And in my experience, these are read-only properties, but it turns out that in the USB spec, descriptors can be writable. And so on the Magic Keyboard, you can actually write USB descriptors over USB, and then they persist in memory until you power cycle the keyboard. And the same is true for a bunch of these HID feature reports. So the way I view this is you have a number of properties on the keyboard that a user can write over USB, and then they stay in that state until you turn the keyboard off and then back on. And around this time, I was also starting to familiarize myself with how the Magic Keyboard pairing worked. And if you have a Magic Keyboard, you plug it in to your Mac with the USB to Lightning cable, and as soon as you unplug it, it's magically paired and it connects over USB. And so I wanted to find out if any of these writable descriptors or HID reports were used as part of this pairing process. So I had a script which dumped all of these properties to a text file. I then plugged the keyboard into a Mac, unplugged it, plugged it back into a Linux computer, dumped the properties again, and dipped the file. What I found was that there were a lot of innocuous changes that looked like maybe counters or flags, but there was one HID feature report which looked particularly fun. This is HID feature report 0x35, and it started out as all 0 bytes and ended as all non-0 bytes. And so this looked fascinating, and I decided to investigate further. And I noticed that toward the front of this, there were 6 bytes which lined up with the Bluetooth MAC address of the Mac that I had plugged the keyboard into. And following that were 16 bytes of high entropy data. And this seemed bad. But at this time, I didn't really understand enough about how the Bluetooth pairing process worked to know if I was looking at something that was actually bad or just appeared to be bad. And in this situation, what I really like to do is go to logging. And I find, one strategy is doing some binary RE to figure out what's actually happening, but I find it's often faster to just look at the logs that some software system is emitting, and it often tells you exactly what it's doing. And so I look at the logs for the Bluetooth daemon on macOS, and it says very clearly that it's generating a link key and sending that link key to the device. So from this, I infer that when I plug the Magic Keyboard into the Mac, it's probably sending out-of-band pairing data over USB to the keyboard. And that's exactly what this is. So the way the out-of-band pairing works, you set an address and a link key to the keyboard, and as soon as you unplug that keyboard, it connects to the host with that address using that link key. And what we can infer from this is that if we have access to somebody's keyboard, and it's to remain powered on, since they've plugged it into their Mac, we can plug into the Lightning port and just read out their link key. And this is not good. But I wasn't sure if the link key was a long-lived key, or if this was some kind of a temporary session key, or what. So I went through this process several more times, repairing and repairing and repairing the keyboard. And on all of these subsequent times, what I found was that the Bluetooth daemon would identify the keyboard and resend the same link key as we see in the logs. And so this means that even if somebody has repaired their keyboard in the future with their Mac, the link key will stay the same and the attacker can still use it. So we have this mechanism to read the magic keyboard over the Lightning board. So again, the attacker plugs into the magic keyboard, just reads hid report 0x35. Once they have the link key, they can then use that to spoof the keyboard to inject keystrokes into the Mac. And around this time, I was also reading more of the Bluetooth hid spec and the USB hid spec. And the Bluetooth hid spec is kind of wild because it has a ton of backward compatibility requirements. And this one sentence here really stood out, and it says, Bluetooth hid devices in discoverable mode should allow the hid control channel and hid interrupt channel to be opened without encryption. And it says encryption, but it really means authentication. And so what this means is when you first power on your Magic Keyboard or any Bluetooth keyboard, it will generally enter discoverable mode where you can have your host then connect to it. But when it's in this mode, anybody can connect to the control and interrupt channels on the keyboard without authentication. And if you think about this, this is probably not good because we know we can read these hid reports over USB. If we can also read them over unauthenticated Bluetooth, maybe we can read the link key from the keyboard over unauthenticated Bluetooth. The problem is, we know when we turn the keyboard off and then back on, those hid feature reports get erased from memory or cleared from memory. However, you can take advantage of a mechanism during this pairing process to actually connect to the Magic Keyboard over unauthenticated Bluetooth and extract the link key. So when we plug the keyboard into a Mac over USB, it's talking only over USB, and the Bluetooth radio is turned off. So it gets the hid feature report over the Lightning USB cable. When the user unplugs the keyboard, it then, excuse me. So when the user unplugs the keyboard, the Bluetooth radio comes online. And as soon as the Bluetooth radio comes online, the keyboard and Mac connect. But there's a brief moment right when the Bluetooth radio comes online where it's in discoverable mode and can be connected to over unauthenticated Bluetooth. So if an attacker is able to time that accurately, they can actually time and target that unplug event, connect to the keyboard, and extract the link key over unauthenticated Bluetooth without needing physical access. And so it turns out this timing trigger actually works very reliably, and we can trigger this very precisely. And so this means that if an attacker is able to observe the unplug event from a physically proximate location, so within Bluetooth range, they can then extract that link key without physical access and inject keystrokes into the Mac. And this is not great because generally you want your credentials going over secure channels. And so now we have these primitives for reading and writing the link key on the keyboard. And I was wondering if we can get the key from the keyboard, can we also get it from the Mac? Because if you remember, the keyboard plugs into the Mac remembers the keyboard, and then gives it the same key. And so I wanted to know, how does the Mac authenticate the keyboard? So I went back to the logs, and I noticed that the Bluetooth daemon on macOS identifies itself as the Bluetooth Super Server Robot Destroyer. And in my experience, when somebody has this level of confidence in their log messages, it probably means they aren't the most, well-established engineer. They probably don't have the best security mindset. And so I was feeling good that there might be a good hack here. And it turns out that the way this authentication works is that the Bluetooth daemon just looks for the Bluetooth address and serial number on a keyboard. And these are things that we can write over USB. So we have a fun attack here, where if we know the address and serial number of somebody's keyboard, we can take a donor keyboard, we can configure our keyboard to have the same address and serial number of the target keyboard, we can plug into the target Mac, it will think we're the victim's keyboard, give us the link key, and we can then read the victim's link key off of our keyboard. So now we have 3 ways to get the link key from the Magic Keyboard of the Mac. We can do it from the link key over Lightning or Bluetooth, and then from the Mac over USB. And just as the macOS can write the link key and address over USB, an attacker can also do this. So we can plug into a Magic Keyboard and cause it to repair to a machine we control. It's also possible to connect to a Magic Keyboard as soon as it's powered on over the unauthenticated Bluetooth channels, send the out-of-band pairing data over unauthenticated Bluetooth, and then redirect the keyboard as soon as it's switched on to a machine that we control. And so with all these mechanisms, I was then thinking, okay, this almost is a good machine in the middle attack. There's one problem where I couldn't get the timing to work exactly like I wanted. So when you connect that unauthenticated channels on the keyboard, sometimes the connection goes through in several seconds, but sometimes it takes a full 25 seconds because there's a timer in one of the state machines which times out after 25 seconds, and so it's not a very smooth machine in the middle attack. But while I was trying to build this out and get this working better, I discovered that you don't actually need to know the link key in the Magic Keyboard to inject keystrokes into somebody's Mac. And the way this works, the attacker can connect to the Mac while spoofing the Bluetooth address of a keyboard that is plugged into the Mac. Then as soon as the victim unplugs their keyboard, the Mac attempts to connect to the keyboard over Bluetooth. But the Mac says, hey, we already have a connection with the Bluetooth address that we're trying to connect to. And so the Mac will instead connect to the SDP service on the attacker's machine as soon as it's unplugged. At that moment, if the attacker tries to pair with the Mac will allow it to pair without authentication, generate a new link key, give that link key to the attacker's machine, and then the attacker is able to then be paired with the Mac and inject keystrokes. And so I tested this against macOS 12, 13, and 14. All were vulnerable. I haven't tested against older macOS because I'm very new to the Apple ecosystem, and I don't have any older Mac hardware. This was fixed in macOS 14.2, but then around the time it was fixed, I reported a bypass in that bug in their fix, and they just last week landed the fix again in macOS 14.4. And so this is what the attack looks like against macOS. This will loop a couple times here. So we see a pairing request that'll pop up. Pairing request is ignored. The attacker is able to then inject keystrokes and navigate to your website. And so why does this work? This is possible due to this no input, no output pairing that I mentioned. And so it's possible to do this attack when several criteria are met. You have to support that pairing. The host has to not prompt when it is using no input, no output pairing, or it has to ignore the prompt, ignore the user confirmation when using no input, no output. And the host has to allow the Bluetooth keyboard to initiate pairing. In the case of macOS, those three criteria are met at that moment that the user unplugs their keyboard. So then I thought, okay, maybe Apple uses common Bluetooth stacks across their OSs. And so I looked at iOS next. But iOS doesn't have that same type of unplug trigger because when you pair your Magic Keyboard with iOS, you just do it through the normal Bluetooth pairing menu. There's no connection with a cable. But it turns out you can do that same timing trigger at the moment that the iPad or iPhone tries to reconnect to its Magic Keyboard. So the attacker connects to SDP service on the target iPad or iPhone. As soon as that iPad or iPhone tries to connect to its keyboard, it instead connects to the attacker's machine. The attacker then pairs with no authentication to the iPhone or iPad and injects keystrokes. So this is similar to macOS in that I've only tested a couple of recent versions of iOS, iOS 16 and 17. 16 remains unpatched. 17 was patched in 17.2. And just like on macOS, there was another bypass to this fix, and they just patched this again last week. So here's a video of what an attack looks like on an iPhone. So I'll hit play here, and then we'll see the keyboard device there listed. That is the actual Magic Keyboard that is paired with the phone. And once we try and connect to that, we'll see that changes to keyboard in quotes, which is the attacker's device, who's then paired and will inject some keystrokes. And we see a PIN code flash by there. That's just ignored due to the bug. And then the attacker is able to inject keystrokes, in this case navigate to a website, but you can perform arbitrary actions as the user, provided that those actions don't require password or biometric authentication. And so after seeing this work on macOS and iOS, it started to feel like it might be more of a Bluetooth bug and not an Apple bug. And so I tried to reproduce it on Android. And Android I have a lot more experience with, and I have a lot more devices on Android, history of devices on Android. And so I reproduced this iOS attack, but what I didn't realize is I'd actually messed up the attack. And I had spoofed the address of a keyboard that wasn't paired to the Android phone. And it turns out on Android, you don't actually have to have the keyboard paired with the phone. The only requirement for exploitability is that Bluetooth is enabled. Anytime Bluetooth is enabled on a vulnerable Android device, the attacker is able to just kind of connect to L2CAP 17 and 19 and start injecting keystrokes. This works whether the phone is locked or unlocked, only has to have Bluetooth enabled. And this I tested all the way back to Android 4.2.2, all the way up through 14. And so this bug has a long history, but it's only been patched in Android 11 through 14 for one variant, and then 12 through 14 for another variant. So after Google fixed the first bug in December, I found a bypass, reported to them, which they then were able to patch last week. The workaround for their initial fix uses a different pairing mechanism. So instead of using no input, no output pairing, it uses what's called display yes-no pairing. And display yes-no is where I say I want to pair with the device. That target device then displays a dialog that says, do you want to allow this to pair, yes or no? On Android, if you first try to pair with display yes-no, you'll get that prompt. If you immediately try again, it will just kind of go through and you can connect without authentication. And this is similar to the first Android bug where it works anytime Bluetooth is enabled. I haven't tested this on as many devices, but I tested it on a selection between 4.2.2 and 14. It appears to have the same age as the other bug. And so now that I've seen this work on Android, iOS, and macOS, it's really feeling like a Bluetooth bug, and so Linux was the next target. And it turns out on Linux you can do the same type of attack. The only difference is Bluetooth has to be enabled, but the computer also has to be in discoverable mode. So on Ubuntu, for instance, this happens when the Bluetooth settings dialog is open, but that'll vary from distribution to distribution. Now what's fun about this bug is actually fixed back in 2020, but nobody enabled the fix. And so the fix required authentication for Bluetooth connections, but it was disabled by default because it had problems with backward compatibility. So all the distros announced that they had fixed this, but nobody actually had. So the fix for this new Linux bug was actually just enabling the old fix by default. So here's what the attack looks like against the Ubuntu machine. So I'll move in a second here. So we have the Bluetooth settings dialog. We'll see the fake keyboard come up. It's now pairing itself. It's now connected, and then injecting keystrokes to navigate to a website. And so in all these cases, the connection and pairing process takes between 2 and 5 seconds, depending on the host. So the fix on Blues was 2 lines. One line was enabling the old fix, and then one line was this comment change. And as a security practitioner, this made me really happy to have something change from defaulting to false to maximize compatibility to defaulting to true for security. And when I saw that, I just felt like I had done some good for the world. And I looked at Windows earlier in the process, and I didn't find any bugs. And after disclosing to everybody else, I finally went back to Windows and found that there is a similar bug, but it's not quite as good. It's not a zero-click attack like the other ones. It requires user interaction, but it's still kind of a goofy bug. So the victim has to have a keyboard paired with their Windows machine. The attacker spoofs the Bluetooth address of that keyboard. The attacker then connects to the Windows machine. The Windows machine will display a notification to the user that says your keyboard is trying to complete pairing or something to that effect. If the user ignores that notification, nothing happens. If the user clicks on that notification, they will then see a pairing request dialog. If they accept the pairing request, it will of course work, but if they reject the pairing request, the attacker's keyboard still pairs. And if they close the pairing request dialog, the attacker's keyboard still pairs. So this I tested only on Windows 11. Microsoft confirmed it on Windows 10, 11, and Server 2022. And they patched this in January of this year. And I also found a bug very similar to this in WebOS. Now this one is a little bit of a different scenario because it's not fixed yet. But it turns out the Android Linux POC works as is against WebOS. So the way I found this, I got a new TV around the time that these were being publicly disclosed. For the first round of bugs, tested it against my LG TV. I was able to connect and inject keystrokes to control the TV. So I reported that to LG, told them I was going to disclose yesterday. They haven't fixed it. Here we are. WebOS is vulnerable. So now I'm going to do a demo against a Pixel 7. This is a Pixel 7 running the February 2024 security patch level. So this does not have the patch that they just rolled out last week, but everything up into that. And so what we'll do, I'll run a script. It is going to connect to this Android phone and start button mashing random key chords, and so we'll see the screen flash and do a bunch of goofy stuff here. And so it's setting random key chords of Control, Alt, Enter, Shift, and then random other hid key codes. And what's fun about this is you can have this idea that somebody can be fuzzing my phone's user interface while it's sitting in my pocket is both kind of terrifying, but also hilarious about these bugs, that you can do this forced pairing at the lock screen even. You can also do it at the lock screen before the user has signed into their phone. So as part of the disclosure process, I had some interaction with the Bluetooth SIG. And they have this stance that basically they make this protocol, they acknowledge that it has these security concerns, but they think it's the vendor's responsibility to care about security and not be vulnerable. And it makes sense because, they're not in the business of security, they're in the business of licensing the protocol. And the more people that license a protocol, the better the business does, and they get more licensees by having more devices that can use Bluetooth. Some devices don't support security. It's in their interest to have support for those devices anyway, and that's how we wind up in this problem. But disclosure bugs between August of last year and January of this year, patches have been rolling out in several groups. First landed in December, more in January, and then more last week. The first set went out to Apple and Google, and Canonical, and Bluetooth, and Microsoft. And the second set to LG, and then Apple again, and Google again. I do want to give a big thank you to Marc of Canonical. He was a huge help in wrangling the Linux side of the disclosure. I hadn't done any kind of multi-vendor open source related disclosures before, and it's not fun. It's hard to track people down, hard to get people to care. But I found that once Canonical reaches out to people, then they care. So that was a very great resource. And so there have been some fallout from this outside of just vendors having to fix things. Fixing the Android bug broke technologies called fast pair and nearby share. Nearby share is their equivalent of AirDrop. Fast pair allows you to discover devices that you could potentially pair with before you're going through the pairing process. And the way that worked initially is they would send signed and encrypted messages over unauthenticated Bluetooth channels. Now, having this unauthenticated channel that they used for fast pair and nearby share, that also allowed you to send unauthenticated communications over USB HID, Bluetooth HID. And so by fixing that unauthenticated mechanism, it broke these other two technologies. And so it took them several months beyond what I expected because they had to do a big vendor rollout of actually implementing and testing all these patches across the Android ecosystem. The Linux bug broke support for things like the PlayStation controllers. There are a bunch of these Bluetooth HID devices which just speak no input, no output pairing. Interestingly, on the PlayStation controller, if you power it on and it's not connected to the PlayStation, you can connect to the controller over unauthenticated Bluetooth HID and then read and write feature reports. So my hope is that there's probably a bug there if we're doing like a malicious DFU over Bluetooth on those controllers. I also found that I have multiple pairs of Bluetooth headphones which I can no longer pair with Linux because they only support unauthenticated pairing. So, through this process, I've been really thinking about what can we learn from this, because at first it looked like everything's just a dumpster fire and nobody does security well, and I was feeling kind of disillusioned at first. And, the vendors, they dropped the ball. They should not have had these bugs. But we as security researchers, we should have found these sooner. These are easy to reproduce bugs. And, I think the reason that people haven't found them is that nobody thought to look. I think when everybody's doing cryptographic research and, kind of sexier attacks like that, I think it's easy to overlook the fact that there might be simple bugs in these kind of protocols. And that's also kind of an uncomfortable thought that, everybody has missed these bugs. But I think that's really encouraging because, we're all humans, we all make mistakes, and I think that means there are probably a lot more of these type of low-hanging fruit, but also really bad bugs in other protocols that we all depend on. And so I just want to encourage you to, think about the different devices and technologies that you depend on every day, that you assume are secure, because everybody assumes they're secure. And I encourage you to just start poking at them and observing how they actually behave, because maybe that behavior is different than you would expect. And that's what I found with Bluetooth, is that I had a lot of preconceptions about how it worked. But it turns out I was only making these assumptions based on other people's opinions, and everyone thought Bluetooth is secure, so I thought Bluetooth is secure. It turns out that assumptions are kind of bad that way. So with that, this is a link to a GitHub repository that has all the POC code, and I am happy to take any questions.
Any questions? Hi, thank you for the talk. Did you have a look at the link key creation process, since it seems deterministic?
So for macOS, the way they generate the link key is just a random number generator within the Bluetooth daemon that generates it and writes it to the keychain and then sends it to the keyboard. And yeah, so
and that's how they save and repeat it.
I'm sorry?
And that's how they save and repeat it.
Exactly, yeah. So it's sorted to the local keychain. I don't honestly have a very good understanding of how the keychain itself works on macOS, but it's just written as a blob in keychain.
Anyone else?
So you said already a little bit about why that security researchers missed this. Do you have any idea why they missed it? What could be the reason? Could it be in the process, or could it be the evaluation, certification?
So what I think is that people, when they're implementing the specification, they are implementing the language that's written in the spec, and they're not thinking critically about was this specification designed well. They're just thinking about, am I going to implement things where I can pass all the unit tests that that are required to be a certified Bluetooth device. But the other part of it is that none of the Bluetooth tooling that I found could implement this kind of attack easily, even though it's only a simple Python script. I had to experiment and really discover just by observing the behavior that this was possible. And I think in hindsight, I could have gone back and read the Bluetooth specification and seen these backward compatibility mechanisms and tested them. But that's thousands and thousands of pages of text, and I think I was intimidated by reading that much text and trying to really digest it. And from my experience, it's really the process of writing tooling to communicate with protocols and interact with devices, and really observing that behavior, which has allowed me to find these kind of interesting logic bugs. I think it's just a different process and mindset than people apply to things like fuzzying for memory corruption bugs.
Any more?
All right, thank you so much.
Thank you.